Stored soil water is measured by the accessibility of that water to plants. There can be water within the soil, but there's not enough of it to be pulled up by the plant through capillary action when the plant respirates. So what we get is first accessible water to a plant is when there is significant water that is adhered to the soil particles, but also to some degree fills the voids between the soil particles. This is capillary water. Water is attached to the soil particles, but the plants are able to draw that water up, and there's enough for that plant to have. Anything that is less than capillary water, where the plant can no longer draw the water up, even though there's water available within the soil, is hygroscopic water. And it's at that stage where you get a wilting point. The plant will no longer be able to uptake that water, and the plant, it will functionally wilt as a result. Adding water then to the soil to fill the voids, doesn't need to be to the field capacity where the soil is completely saturated, but to the point where there's capillary water, so there's enough pressure that that plant can bring that water into its vessel, into its cellular structure. When water continues to be added and 100% of the void spaces or the pore spaces between the particles is filled to 100% capacity, then you have field capacity as is met. So we've got 100% of those voids are filled at that point. The structure of the soil, how the individual particles are formed and shaped, will determine the amount of water that the soil can hold. So the soil type, is it a clay? Is it a loam? Is it sandy? Is it silty? Is it a combination of a silty loam or a sand and clay combination? Will determine how much water can be housed within the soil between those particles, and what the uptake of that water will be. How readily can plants draw out moisture from that water? So if we look at the gamut of structures, we could look at clay, which is a very, very fine and very flat type of soil particle, results in the soil particles being able to stack on top of each other, kind of like papers when they're stacked on top of each other. There's not a lot of room between the particles. This means there's not a lot of room for water within that soil. This is why we were able to make pottery and cups and plates out of clay, is because the matrix of the soil is really, really tight. When the water, or when the clay is at field capacity, that clay can swell and still retain and hold moisture back from penetration. So a lot of dams, earthen-filled dams, are made out of clay for this very reason. Sand, on the other hand, is the opposite. It's mostly spherical shape. It can be irregular, and it creates out of that spherical shape a lot of pore spaces. This means that a lot of water can be held, but that the water can also easily run through that clay. And anybody at the beach who has watched the tide go in and out can watch the water drain out of the sand pretty readily. So with soil particles, with the diagram shown in this slide, you can see that clay has a really, really tight matrix. Those little particles can be really close, but there can still be a really high capacity to hold moisture within that. We move from clay, which is small, to silt, to sand, and then to gravels. Those are the general size characteristics within soils. There are a whole bunch of other combinations that could be illustrated, but these are the primary four. All right, so we know that clay has high pore space but low permeability. That means that you can't permeate or pull water into those clay particles, even though it can store a lot of moisture. Likewise, sand, on the other hand, not quite as large as gravel, will then have a moderate pore size and high permeability. We can really pull moisture in and out of that soil structure that is a sand. So this illustration then just gives us a really lovely illustration of what we've got with the ability for water to be housed within soil particles, what is considered field capacity. In this diagram, what is also noted is that you will find gravitational water right here in this portion of the slide. Gravitational water takes place when 100% of the pores are filled. When they're filled, then gravity will draw that moisture down to the next layers of the soil structure or the rock structure. So when it rains or when you're irrigating your lawn, the first little layers get filled, and when they're filled to 100%, then that water travels to the next layer down. When that layer is filled, then it'll travel to the next layer down, and so on and so forth. So that is how we draw moisture into deeper levels of soil and eventually deeper and deeper levels of rock structures. So that gravitational water then is the mechanism of pulling water down to those deeper layers, and that mechanism is known as percolation. Percolation is the filling up of a pore and then moving that water down to the next available pore space, and then filling that pore space up to 100% and then pulling it down to the next pore space. So that is percolation.